So here I'm going to discuss conservation of momentum. And conservation of momentum in explosions sometimes is a little counterintuitive. So you have like a bomb and it's not moving at all and it has some mass. And then all of the pieces sort of explode out away from this bomb. And they all have mass and they have all velocity. So how is momentum conserved in this case, where you start with a momentum of 0 and then you've got all these little parts that have their own individual momentum? Well, the reason is because momentum is a vector. So remember that velocity is a vector and it has a direction. So all of these parts are radiating out away from the center, and therefore their net momentum is 0 if we were to add up the momentum of all the parts. And I'm going to do some sample problems in this video too. So next we have the idea of collisions, and we can have either elastic collisions or inelastic collisions. Elastic collisions are when two objects collide and they bounce off one another. But in particular, if we are to say that something is perfectly elastic, we say that kinetic energy is completely conserved as well as momentum. And if you wanted from a scenario to actually determine if elastic collision was really elastic when two things bounced off each other, or perfectly elastic, you would have to prove that the kinetic energies were the same, not just that they bounced off one another. Now, an inelastic collision is actually when kinetic energy is not conserved, and most often these two objects will stick together after the collision happens, but not necessarily always. So somehow that kinetic energy has been lost to some other form. It might be sound, it might be heat, all sorts of different places the energy could have gone, and we'll do some examples of inelastic collisions as well. So one thing to keep in mind is that when we calculate energy, energy is not a vector. It does not have a direction, whereas momentum is, and it does have a direction. So if we look at this equation for momentum or conservation of momentum, it's this big, long, messy equation, and it looks very intimidating, but I'm going to do some examples, and really, I just want you to keep in mind that momentum is conserved and not write this down or even really think about this big mess or trying to memorize this big mess of an equation. It's really sort of common sense. So I'm going to use the Elmo and we're going to do some sample problems. So the first one that I'm going to do is the idea of an explosion. So it's not really an explosion, but it's the same general idea. So you have a person sitting on a boat and they have a package and they're going to throw that package off of the boat. And the mass of the package is 5.4 kilograms. And the velocity of the package after it's tossed is 10 meters per second. And so we know that the boat would then move back. And so we want to know what velocity is the boat going in this direction. So we know that momentum is conserved. Initially, the whole system has a velocity of 0, right? So a person's just sitting at this boat at rest. And then they throw the package this way. So we know that all of the momentum to the left has to equal all of the momentum to the right. So if we think about the momentum to the left, we have to calculate the entire mass. So it's the boat and the person together times the velocity has to be equivalent to what's happening to the right, but just in the opposite direction, right? So we've got the 5.4 kilogram package moving to the right at 10 meters per second. So we want to see, well, what velocity makes these equivalent, and we know that that velocity would be in the negative direction. So 5.4 times 10 gives me 54, and then we're going to divide by 26 plus 55, what's that, 81? So we're going to divide by 81, and I get 0.66 meters per second. So the velocity of the boat and the person is going to be 0.66 meters per second, and we can say that's negative or to the left. All right. Now let's look at some examples of collisions. First, let's start with an inelastic collision. So in this case, I've got two train cars, and really what we need to think about is the scenario. What's happening before the collision and all the momentums before the collision, and then what happens after the collision. So before, I have two train cars. I've got one that's going 24 meters per second to the right, and I've got one that's just sitting still, and its velocity is 0. After they collide, they stick together. So now they're one thing, all moving at the same velocity. So if I was going to write that equation, I would say, okay, well, the mass of thing 1 times the velocity of thing 1 at the beginning. If I add that to the mass of the second thing times its velocity at the beginning, that's got to be equivalent to, well, they're stuck together now, so their total mass, and they only have one velocity. Now, I know that thing 2 is just sitting still, so this term actually completely cancels out. So all I would have to do is say, okay, well, the mass is 1 times 10 to the 4th times the velocity is 24. And that has to be equivalent to mass 1 plus mass 2, so that's going to be 2 times 10 to the 4th times V final. Okay? And then I just have to solve for V final. So let's go ahead and put this in. So 1 EE to the 4th times 24, and then divide that by 2 second E to the 24th, or sorry, to the 4th. And I get my V final is 12. So notice I have doubled the mass and it has halved the velocity. So in this case, my V final here would be 12 meters per second to the right. Now remember I said in inelastic collisions, kinetic energy is not conserved. So quite frequently you might be asked to calculate the loss in kinetic energy. Well, that's very simple to do. All we need to do is calculate the kinetic energy at the beginning of the scenario of all the objects, and the kinetic energy after the collision for all of the objects, and then subtract the two, and that would be the difference, or the loss in kinetic energy that has gone somewhere else. So I know kinetic energy is 1/2 mv squared. So I'm going to do 1/2 of 1 times 10 to the 4th, then 24 squared. I'm going to say that isn't equal to what this is at the end, but we're going to get this value and then compare them. So at the end, I've got 1/2, and then the mass is 2 times 10 to the 4th, and then the velocity is 12 squared. So let's figure out what those are. So 0.5 times 1e to the 4th times 24 squared. And that gives me, 1, 2, 3, 4, 5, 6. So 2.88 times 10 to the 6th joules. Okay. And then over here, we're going to calculate this one. So we get 0.5 times 2e to the 4th times 144, and this is 1.44 times 10 to the 6th joules. So we know they're not equal, and so if we were to subtract them from one another, we could figure out the loss. And the actual loss in kinetic energy in this case is going to be 1.44 times 10 to the 6th joules. So just subtracting this number from this number. Alright, so let's look then at an elastic collision. So the first example, let's go ahead and look at where two objects are moving towards each other. So you have an elastic collision where they come and they bounce off one another, but it's not necessarily perfectly elastic. And this one will prove that it is perfectly elastic using kinetic energy. But for this one, let's just use our conservation of energy equation. So what I need to do is I need to figure out, the conservation of momentum equation. I just need to figure out the momentums at the beginning and set them equivalent to the momentums after the collision has happened. So remember that it is a vector, so I have to take into consideration the direction. So here I'm going to have 340 times 1.2. And then here I'm going to have, and I guess we can put it in kilograms. Let's do 0.34 times 1.2. And then I'm going to add to it 260, or 0.26. And I'm going to multiply that by a negative 0.7 because it's going to the left, right? And that has to be equal to the mass, or the momentum after. So now I've got this object going 0.3, or that's 0.34 going a negative 0.8 meters per second. And that has to add to 0.26 times my V final. So I want to know how fast this guy is going, right? So it's just some simple algebra. I take 340 times 1.2, and then I'm going to subtract from it 0.26 times 0.7, and I get 407, oh wait, hold on, that needs to be 0.34, sorry, I knew that looked a little weird. So 0.34 times 1.2, and then we're going to subtract from that 0.26 times 0.7. And so on the left, I get a momentum of 0.226. And then over here, I've got 0.34 times 0.8. That's going to be a negative number, negative 0.272 plus 0.26 V. All right, so just have to add those two together. So 0.226 plus 0.272, and then divided by 0.26, and I get my final velocity is 1.9. So 1.9 meters per second, and it's positive, so I know it's going to the right. Okay. So again, it's just about adding the momentums at the beginning and the momentums at the end. So let's just do one quick more problem. So in this case, I've got an object that's moving to the right at some velocity the same as it was up here. And this object is sitting still, and it has to be equivalent to these momentums at the end. So I have 0.34, its momentum, times 1.2. This is going to be 0. Has to be equal to, and it says this one keeps going to the right after it strikes the car at rest. So 0.34 times 0.66, and I want to know what velocity this thing's going. So that would be 0.0987 times V final, right? So 0.34 times 1.2, that gives me 0.408 is equal to 0.34 times 0.66. I'm going to subtract that from the previous number and then divide by 0.0987, and I get my final velocity being 1.86 in this direction. Alright, so let's go ahead and prove that conservation is then conserved, because if kinetic energy is conserved, then I know that this is a perfectly elastic collision. So I just need to add up the kinetic energy. So 1/2 of 0.34 times 1.2 squared is going to be pretty equal, minus some little issues of rounding, of 1/2 of 0.34 times 0.66 squared plus 1/2 of 0.0987 times 1.86 squared. So for the first one, I get 0.2448 joules, and for this one, let me just write this out, and then 0.5 times 0.097, and then times 1.86 squared, and I get 0.1707, and I'm going to add that 0.074 to it, and I get 0.2447. So with a little bit of rounding, they are, off by like a 10,000th of a point, but they are pretty close. So this actually proves that this was a perfectly elastic collision. Okay? Anytime kinetic energy is not conserved, that means it's not perfectly elastic, and there was some inelastic quality, even if the objects bounce off one another.